Welcome to our paper Event-Aided Direct Sparse Odometry, the first direct method using events and frames. Events and intensity frames are complementary sources of visual information. Combining them has proven useful to improve accuracy and robustness in several tasks, such as image reconstruction, feature tracking, video frame interpolation, and camera motion estimation. We also seek to get the best of both visual sensors for SLAM-related tasks. Event-based visual odometry is a challenging problem mainly because events depend on motion, causing a change of appearance. Previous work, such as Ultimate SLAM, ignored this problem by processing events and frames separately and fusing their key points late in the backend. However, this makes event-based key points difficult to detect and track with sufficient stability. Until now, no effort has been made in VO system to fuse the same key point seen by both sensors. We introduce EDS, a direct monocular visual odometry method with events and frames. EDS overcomes the problem of change of appearance by design, and fuses events and frames in a principled manner in the front end by exploiting the event generation model. The following diagram summarizes the methodology. We assume a camera, shown here on the left, that provides synchronized events and frames on a common image plane. The frames are processed by using the grayscale values in the logarithmic of the intensity, L hat. Afterward, the gradient in x and y direction is computed using the solver operator, and a set of sparse pixels is selected based on the gradient magnitude. A set of pixels is used to calculate the brightness increment, delta L hat, by applying the event generation model, which computes the dot product of the gradient and the pixel displacement. This is a function of the local optical flow and therefore the inverse-dead parametrization of each pixel. It is denoted here by the 2x6 Jacobian matrix J. Simultaneously, the events are integrated considering their polarity and forming a brightness increment frame, delta L. The events are weighted using an exponential window to assign the relative importance to events depending on the order of arrival. The highest score for events is located in the middle of the time window. Such a window can be a sliding window with arbitrary duration and overlap. Finally, we can compute the brightness increment error, the difference between the normalized brightness increment model and the measured brightness increment over a sparse set of pixels. The optimized parameters are the delta relative position and orientation and the instantaneous linear and angular camera velocities that minimize the error. We evaluate the method's performance in sequence from the standard RPG Davis stereo dataset. Data were collected with a handheld stereo camera in an indoor environment with ground truth poses from a motion capture system. We use the left camera since our method is monocular. The results show a smaller absolute translation and rotation error with respect to the previous event-based methods and are in line with the state-of-the-art frame-based method. EDS outperforms state-of-the-art frame-based methods in the DES sequence. This is because traditional two frames direct image alignment assumes a simple constant velocity model to initialize the tracker at every new frame. However, by including events, the solver minimizes the nonlinear photometric error with a more accurate starting point. EDS is more robust at lower frame rate experiments than frame-based methods. This is because EDS can continuously track the camera motion in the blind time between frames. When a new frame is given, classical photometric optimization triangulates new points without losing camera tracking thanks to the events. It opens the door to sparingly trigger frames on demand and tracks the motion in between. We conducted a sensitivity study, released the code, and a new dataset with events, frames, and inertial data. Please check the paper for details. In conclusion, EDS is the first direct visual odometry combining events and frames. The results are more accurate than previous event-based methods. Events improve classical photometric image alignment in frame tracking and open the door to low-power motion tracking applications where frames are triggered on demand.